In this video, we're going to learn how to check the conditions for inference when we're talking about regression. So these look pretty different from the ones that we were using for ANOVA, but we'll see later that they're actually related in some ways. So let's think about how the regression model is set up. So basically, we have our response variable y, and we can write it in terms of the beta. So beta 0, that's the population intercept, beta 1, that's the population slope times x. So you can sort of think all of that is fixed, right? There's only one population intercept, there's only one population slope. So the part that's actually varying is this little epsilon out here. These are the residuals. So the residuals are the difference between the individual data values and the values that would have been predicted based on the regression line. So if we think of it in the sample, the residuals that are above the line, those would be positive residuals. And the ones that are below the line, the data values that are below the line, those would be negative residuals. So since the residuals are the only part that's actually going to vary here, since the slope and intercept are fixed in the population, it makes sense to check our conditions in terms of the residuals. So we're making the assumption about how the residuals are distributed. So we're assuming that they have a normal distribution. So if you look at any given point on the x-axis, we're assuming that the y values would be distributed normally. And that's in the population. Obviously, that's not going to be the case in the sample, but we're imagining that if we took enough observations that we would see this normal distribution. We're also assuming that the residuals have a mean of 0. So that means you don't have more residuals above or below the line, that they're balanced. And also that we have a certain variance and that it's the same no matter where you are on the axis. So the spread of the points around the line doesn't change for different values of x. So those are our assumptions in terms of the residuals. Now let's think about how to check them. So the first one is just sort of going back to that regression equation itself. We're assuming that the association between y and x is linear in the population. So of course you can look at linearity in a regular scatter plot, but sometimes it's easier to see this in a residual plot. So what this plot is we've got our residuals on the y-axis, and then our explanatory variable is here on the x-axis. So what you can sort of imagine is like if you took your regression line and you pulled it down so that the regression line was flat, right? Because all the points above it, those are positive residuals, so they would be above 0 in the residual plot. All the points below it are below 0. They would be negative residuals in the residual plot. So we're just kind of pulling this down to make it easier to see the residuals. So what we want to see in a residual plot is just a nice random cloud of points around 0. So this first graph here, this would look pretty good. This would be like a linear relationship because you don't see any kind of curved pattern. The second one, we've got definitely a curve in the residuals, and so that would indicate non-linearity, that you've got, positive residuals in the middle here, so a bunch of points above the line where the regression line seems to be underestimating. And then you've also got these negative residuals on the edges, so that means the points are below the line and the model is systematically overestimating. So we don't want to see non-linear relationships like that. So when I look at this residual by x plot for the BMI data, I don't see anything like that. I don't really see any curved pattern. So I think this one looks pretty good. I think it's reasonable to assume that we have a linear relationship here. The second condition is just based on the study design, that the data are gathered using some sort of randomization and that the observations are independent of each other. So remember, the types of conclusions that you can draw depend on the type of randomization that you have. So if you have a random sample is going to allow you to generalize to the population. And if you have random assignment, then that's going to allow you to make cause and effect conclusions. So when we're dealing with regression, I would say it's more common that we have random samples, that our goal is to generalize to the population. Of course, there's some crossover, but a lot of times we're dealing with observational studies here. So we're talking about the Framington study, and we don't have any information about whether it was randomly selected or not. So that could potentially limit our generalizability, right? We can only generalize if this sample is actually representative. So we would need some more information about the demographics of who participated in this study to decide if we can actually generalize to the whole population. Third condition is that the spread of the residuals is the same at any point on the x-axis, that it doesn't depend on the explanatory variable. And this is related to the assumption that we made in ANOVA, that we have the same population standard deviation in each group. Here we don't have groups, we just have different values of the explanatory variable, but it's the same basic idea. So the way that we look for this one in the residual plot is that we're hoping to see the same vertical spread at all points along the x-axis. So if you see the same vertical spread everywhere, then that would mean that you have constant variance. What we're concerned about is graphs like this, where you have really small spread on one end, like you've got really precise estimates on one end, and then it's much more flared out at the other end. This would indicate non-constant variance. So this would be a problem with our assumptions because it seems like the residuals, the spread of the residuals, changes based on x. So looking at this residual by x plot for the BMI cholesterol data, I don't really see any weird shapes. It looks fairly even all the way across. In particular, that funnel shape that we look for, I don't see anything like that. So I think it's reasonable to assume that we have constant variance in this example. And the last one listed here is that the residuals are normally distributed. So there's a couple different kinds of plots that we can look at. One of them is a QQ plot. So I'm not going to go into all the details of what this represents, but basically a QQ plot compares your real residuals from the sample to the residuals that you would have expected if you had a perfectly normal distribution. So what you want is a straight line, because that would indicate that the residuals from your real data are the same as what they would be from a normal distribution. But sometimes it won't come up exactly straight. So if you see something like this, where you've got like a curve around the line, that would indicate some kind of skew. And specifically this one, where it's kind of dipping below, that would indicate right skew. If you have like an S shape or a backwards S shape, this would indicate that you have the wrong weight in the tails. In other words, the amount of extreme values in the residuals is not quite what it should be. So looking at this QQ plot from JUMP, we can see it actually gives us, besides the straight red line, it gives us some little red boundaries. And that helps us to tell whether the values fall further away from the line than we would expect if the data were actually normal. And here it does seem like some dots fall outside of that line. So it seems like this isn't just a little bit of random variation. It seems like this is probably not a normal distribution in the residuals. And we'll talk more as we go about how this really affects the outcome. So for some things, the sample size can overcome any issues with the shape, right? We've talked about how things like t-tests and f-tests are fairly robust to non-normality. So in terms of inference, I wouldn't worry so much, but there's other things where the non-normality causes more of a problem, and we'll talk about that later. Let me quickly show you how to get these residual plots in JUMP. So we already have the linear regression for the BMI data just by doing fit y by x. We're going to go down here where it says linear fit, and we're going to go to plot residuals. And this will give us several of these graphs all at once. So let's start here at the top. So this is actually a residual by predicted plot. So this is a little bit different than what I showed you earlier because it does have the residual on the y-axis, but the x-axis are predicted values instead of the explanatory variable itself. And we'll talk about why there's some benefits to that, but reading it is the same thing. You're still looking for any curve that might indicate nonlinearity or any funnel shape that might indicate non-constant variance. This also has a histogram of the residuals here. So we can see that skew. Remember we said earlier that we were worried about non-normality. We can sort of see that skew here, and this is actually right skew because the tail is going towards the larger values. The actual by predicted plot and residual by row plot, we haven't really talked about those. Residual by row, that would be more if you had like a time series or something and you were worried about independence. Here's our residual by x plot that we discussed. And here's that normal QQ plot. So we can see we've got the little curve that indicates non-normality. That's consistent with the histogram. All right, so this is going back to the house prices data. All right, so I'll give you a second to pause the video and think about which, if any, of these validity conditions do you think might be violated? All right, linearity, I'm not really worried about that. I don't notice any like curved pattern or anything like that when I look at the residuals. It looks pretty much symmetric on both sides of 0, so I think linearity is a reasonable assumption. The one that I'm most worried about is constant variance, or the fancy word for that is homoscedasticity. So if we look at it, I'm a little bit afraid there might be a bit of a funnel shape here, right, where it's a little bit more precise estimates down on the low end and less precise on the high end. So that would be the one I'm most worried about. To be honest, it's a little bit hard to tell because it's a pretty small sample size, but that's something I would be concerned with. Normality, it actually looks pretty good. These points are falling nice and close to the line. And jump output actually helps you out by giving you these dotted lines as a guide. So the fact that you don't see anything outside of those dotted lines would indicate that there's no reason to think that this isn't normally distributed. And I didn't mention randomization here because that's one that you check based on the study design, not based on the residuals. But this is another example where it doesn't tell us that the houses were randomly selected. So again, generalizability is questionable.